It's my pleasure to introduce one of the two Rothschild public lectures we had associated to the RCL program. And today he's going to be given by Professor Subhashis Ghoshal from North Carolina State University. Subhashis is one of the leading figures in the area of non-parametric, Bayesian non-parametrics and high-dimensional statistics, incredibly highly cited researcher, and he wrote an influential textbook in 2017 with Ard van der Vaart, which won the De Groot Prize. And today he's going to talk to us about Immersion Posterior. It's you.
Thank you very much, the organizers, the Newton Institute, for inviting me here. It's a tremendous opportunity, and especially selecting me for the Rothschild Fellowship. It's a tremendous honor for me. So today's talk, I would talk about a concept that would like to formalize to aid Bayesian inference in certain situations, and that would hopefully solve some of the more difficult problems that we encounter. So, and this is a public lecture, so I start with very basics. Probably this slide is something that is kind of redundant, but nevertheless, just spend a minute or so. So the Bayesian paradigm of inference, one of the most influential paradigms in statistics that are adopted, is based on a straightforward probabilistic approach to uncertainty. So this originated from a relatively innocent theorem by Thomas Bayes, just on conditional probability, but it has huge implication in that it framed the way of thinking about statistical inference that influenced the many work. So in terms of in the descriptions, you start with some prior distribution that's supposed to quantify the knowledge or uncertainty about your unobservable parameter in terms of a probability distribution, and then you have a model description that is put here in the form of a likelihood. You make it the conditional probability is the data given x, given by this formula, and then you use this to make inference. Now, of course, this is just a basic description, but there are always challenges in how do you specify prior, how do you compute this, and then theoretical analysis. The really attractive aspect of Bayesian inference is the straightforwardness of the solution. So you just have to specify these things, and then the path is automatically shown. But what is nice can also be a problem, the rigidity that because once the prior is specified, you don't really have any freedom. It just has to be this. And if this doesn't work, then there's a constant. So in reality...
What do you mean by whether or not that works? What does it mean to work?
So one thing is the frequentist properties, that there's reason, we'll not discuss into that, but there's enough reason to look at whether this procedure that we formulate has some reasonable or optimal frequentist properties, and that's where it may not be the right thing. So that is the primary goal, but there are other problems that can also arise in some situations. So primarily I'll be talking about I'll be concerned about frequentist properties of Bayesian procedures. So this is just a basic description, but in reality it doesn't quite work in that way. The prior is supposed to be based on your actual prior information formulated in terms of probability distribution, but that is never an easy process. So in reality, what we do is we choose something according to mathematical convenience and use our pre-experiment information to choose some key parameters, or maybe if we in most cases we may not even have that, so we choose something that is sort of non-informative. So this is not exactly the prior in the purest sense that we use in practice. And then you may need other modifications. So for example, we often, especially in non-parametrics, we use the sequence of priors, or sometimes even data-dependent prior, although it's less common. So these kind of modifications are often needed to make things work. Another thing is you modify the likelihood using something deliberately misspecified. So for example, in the regression problem, so you may put the normal as the working model, even though you know probably it's not the right thing, but it's just convenient and it gives good solutions. So that's how you can use it. Or in some problems, you may not want to condition on the whole data because that does not give you very good behaving posterior, but you, for some reason, so for instance, you may want some invariance property and you just condition on part of the data. For example, by conditioning on the ranks, it's automatically invariant. Or you can distort the likelihood by raising it to a power. That's called tempered likelihood, or even more generally, something based on a loss function, often known as Gibbs posterior or PAG Bayes. And even something not quite Bayesian, but has some structure that are inspired by Bayesian formulas. So examples of predictive recursion, martingale posterior. So people have tried this. And finally, the last one I would mention is variational Bayes. We'll come back to this later on. So variational Bayes is sort of approximation to the posterior, supposed to be an approximation, but in reality it's actually not. But it's very useful because it can be computed very quickly, and in machine learning applications that's used, is very frequently adopted. So our objective is to add another flexibility to Bayesian paradigm through this, what we call the immersion posterior, within the logical structure of Bayesian inference. That is, the logical structure is to come up with some sort of random measure based on prior and posterior that you can use to make inference. So the immersion posterior, what it does is it adds an extra degree of freedom that can be combined. It's not exactly a competitor to other modifications like empirical Bayes. It can be combined with any other modification. And we also want to give some Bayesian interpretation of this immersion posterior. And for most part of this talk, we'll talk about, we'll describe some examples where we'll show usefulness of this approach. So start with an example like stationarity in time series, like autoregressive or ARMA processes. So the condition for stationarity involves some restriction on the coefficients. Especially in vector autoregressive ARMA processes, these restrictions can be really complicated. So if you have to put a prior on a stationary time series, you'll have to comply with that complicated restriction. But nevertheless, that's parametric, not too difficult within the usual Bayesian framework. Then I give some non-parametric example. So shape restriction for functions. So function often arises in inference. The function is itself the parameter. So for example, a regression model, you may have a regression function that is known to be increasing. And this is a very useful information that can be used to make inference about the function. You can also have decreasing density, for example, it in one variable or more than one variable. Convex regression, the regression function is convex in the argument. Log concave density. So these are all shape restrictions. And in non-parametric function estimation, the usual way of doing is assume some sort of regularity, smoothness, for example, and then you have to smooth, but you have to tune how much smoothness you have. With shape restriction, that additional information allows you to do inference and optimal inference without actually having a tuning parameter. So that's another type of regularity. So that's useful structure, and often it's appropriate in modeling. Next example is a differential equation model. So this is a nonlinear regression model. The function involves some parameter, but the point is that the function is not explicitly given. It's only given implicitly through as the solution of some ODE or PDE, where that ODE or PDE involves this parameter theta. So here, theta, the parameter space is theta, and then for every theta associated, you have this function. The problem here is that the evaluation of the likelihood is difficult, because every time you want to evaluate at some theta, you will have to solve that differential equation which has no explicit solution. So these models are very common in PKPD applications and few other situations. The last example I give is sparse regression. So you have a regression model with a lot of predictors, and I illustrate with just a linear, but it can be something more general. And you can have the number of predictors even more than the sample size. So this is not exactly estimable in that sense, but with the assumption of sparsity, which means most components of theta are 0, then it's possible to estimate this. So in this context, so we look at this. So in this first situation, this is the class of all functions, and within that we have class of Morton functions. That's a subclass form that is our target parameter space. In this context, we can look at theta as the parameter space, but that computation is complicated. So instead of that, we can look at these functions indexed by theta as our parameter space. And finally here, in this, generally speaking, you can have any theta, but then you are targeting the sparse vectors. So that's sort of a subset, but not exactly a well-defined subset. It's more like a fuzzy subset. So these problems have something in common. That what I exactly described, that you can view the problem, the parameter space is being some sort of part of something bigger, where the model still makes sense. So in such a situation, if you have to incorporate the restriction, it is a useful information, but incorporating that makes the inference complicated, because the prior that you construct will have to comply with those restrictions. That is not the main problem. The main problem is that leads to a complicated posterior, which is difficult to analyze theoretically, which is also more difficult to compute. So if you didn't have that restriction, then you have less information, but you could have done something simpler. In the bigger parameter space, without the restriction, you typically have something simple prior, like based on conjugacy. So computation and analysis is often you will have explicit expression for the posterior distribution. So an immersion posterior that I'm going to introduce is designed to solve problems like this and will give the motivation, interpretation, and comparison and describe some properties. So the key idea is to ignore the complication due to the structural restriction and work with the unrestricted prior on this larger space. On this larger space theta rather than theta 0. So what you get is a simple posterior. Of course, this is not the posterior you want because you want the posterior to sit on theta 0. So what you do is you, if you just compute or like you can get samples from this because this is a very simple, so you can get samples from this posterior distribution. But your target is some distribution on theta 0. So what you do is you use a transformation from theta to theta 0, which we call the immersion map. And this transformation will convert these unrestricted posterior samples to the samples that complies with the restriction, that is live in theta 0. So that gives you an induced distribution, another random distribution given the observation. And that is what we call the immersion posterior. So in most cases, its computation is sampling based. So you just sample from the unrestricted posterior and then apply this map to get samples from the induced posterior distribution, from the immersion distribution. And once you have sample, you can do anything. So you can construct estimator, you can construct credible regions, you can do testing, whatever. Okay, so as I mentioned, this is called the immersion posterior. And one most obvious example of immersion map is a projection map. So for example, in the case of this monotone functions, so we can have, we can put a prior distribution on space of all functions without the restriction, and then we can have some sort of conjugate prior based on basic tools of non-parametric base, such as binning and then putting a prior on the state functions. So we get a very simple posterior distribution, but that doesn't comply with monotonicity. So you isotonize every sample from that, and then that isotonization is finding a function that is closest to the original function within the class of monotone functions with respect to some distance like L2 distance. So this is like finding the closest point or projection to the target space. So that is called a projection map, and this special case of projection, in that case we call the immersion posterior to be projection posterior. So what we are doing essentially in immersion in the traditional base, we have this restriction, this model, and then we are supposed to follow some restrictions. So when you put the prior, you put a prior so that this theta star that complies with the restriction, and then you update to the posterior distribution. But because this is already complicated at the prior stage, the posterior is even more complicated, and it is hard to analyze this. It's also occasionally quite difficult to compute the posterior. So what we are essentially doing is that, okay, so let's do this thing first, the updating first. That's simple. And then this is also simple, so this composition. So obviously we don't get exactly the same thing. So we get a different random measure. So as long as we can show that it has some nice concentration properties and this, so this can be useful in making inference, at least from the frequentist measurement. So what do we lose? We definitely lose the definiteness of the Bayesian approach. So now, in addition to the prior, we will also have to choose a map. But it's no harder than choosing a prior or loss function. So in particular, in some cases, it's kind of very natural what should be the map. So for example, in case of monotone function, if you got a function, you want to make it monotone, just find the closest monotone function. So that's not really hard to imagine what can be a transformation. But what do you gain? You gain an additional degree of freedom that can be combined with all other modifications that have been proposed. So, for example, improper prior, empirical base, pseudo likelihood, misspecified likelihood, conditioning on statistics, inflating a credible region, anything that has been considered, you can combine this with that, and you can use different immersion maps for different purposes. And in fact, we'll see that it is actually needed to optimally to get optimal solutions. So I see this like this. So it's not a completely different object. So like I have an impaired vision. So if I try to see without it, I will see blurry things. But if I put on my glasses, I see it clearly. So it's just like a correction that if something is not working, you use this device to make it work. So I'm coming back to variational Bayes. So variational Bayes was originally proposed as an optimization-based computational device, alternative to MCMC. So this is very useful in large-scale applications. But in reality, there's not much results on approximation that is available. What is really available is some sort of convergence result. So in what it gives us and some sort of alternative random measure that you use to make inference, just like immersion posterior. So in that sense, they are very comparable and similar. So because you don't get really the posterior as approximately, so some sort of frequentist justification is desirable. In fact, even for the whole Bayes, there is enough reason to look at frequentist justification. And in this context, the main goal is to obtain good frequentist properties. So that's why it should be there for variational Bayes or immersion posterior, because we are looking at some alternative measure. For variational Bayes, there are convergence theorems, but hardly anything on frequentist validity of uncertainty quantification given by variational Bayes. So in case of immersion posterior, which is just like another alternative random measure, and which is also computed by this map. This map is often described by optimization. So for example, isotonization, that's an optimization, but it has explicit solution. There may be more complicated ones. So we want to give some sort of a convergence theorem for immersion posterior, just like there are some on variational Bayes. Now, for optimization, for variational Bayes, the optimization is done at the distributional level. So this is typically a little bit harder and iterative. In case of immersion posterior, the optimization is done at the parameter space level, which is typically much smaller set, and it's typically non-iterative. So on the other hand, it has to be done several times, whereas for variational Bayes, you just do it once or a few times. But the point here is that one advantage IP has is the simple description, representation. So because of that, we'll see that we often can validate the IP uncertainty quantification from frequentist angle, which is not quite so easy or not available for variational Bayes. And then talking about Bayesian interpretation. So we can give a Bayesian interpretation. So we want to stay within the Bayesian paradigm, not drastically depart from there. So you can think like this. So there is some sort of super parameter, which really something fictitious, and you just view the parameter, target parameter, as some sort of functional of that super parameter. So what you do is, because our basic assumption is that the model makes sense in a broader sense. So it makes sense when it's indexed by the super parameter. So that's what I would denote by this. And then the original model is this. So theta is just some sort of functional of this super parameter. So what you do is you use this model, even though you know that this is the model, you just use this model to construct your posterior distribution, because that's easy. But at the end of the day, it's not eta, but theta you are interested in. So this is the functional of eta. So you should look at not the posterior distribution of eta to make inference, but that of the induced posterior distribution. That is the immersion posterior distribution. So that is what the Bayesian interpretation is. So what we see is that IP is a genuine conditional distribution, unlike empirical Bayes or variational posterior. So certain logical consistency will always be there. So for example, it satisfies the likelihood principle. And there's no double dipping of that data, unlike empirical Bayes, unless you use the immersion map dependent on data, which is also, by the way, allowed. And immersion map need not be a projection map. Projection may be just one natural one, but sometimes you need to go beyond that. So for example, there may not be any associated natural distance. And if there is no natural distance, there is no natural projection. So for example, you want to make inference about the function value at a point, then global metrics are not really appropriate. And then there are certain things we want to look at more broader sense. It's not necessary that I theta, in case of projection, if you project, projection has idempotency property. So if it's already compliant, you don't change it, right? So that's fine, but it doesn't have to be that way. It's not necessary that your target parameter space is a subset of theta. It's some theta that, big theta is that something, some alternative space where you can think about the model. So it doesn't have to be, because the immersion map can be just some map. And it's not needed that immersion map is defined all over theta. What is needed is it's defined on the support of the posterior distribution. So what you need is an alternative parameter space where this model makes sense, a prior on theta, which is computable posterior distribution, typically aided by conjugacy, and good frequentist asymptotic properties, because that was the main motivation for doing this. And we can combine it with any other posterior or pseudo-posterior. So in most examples, we consider there is some way to use conjugacy, and that's always desirable, but it can be from samples obtained by rejection sampling or from MCMC. And what we'll see is that if we extend Bayesian paradigm in this way by this additional map, then the scope of conjugacy is actually much broader. So typical conjugate solution may not be available in some models, but here with this immersion map, it would be available. And there are more leniency, like dependence on sample size can be allowed, the immersion map, or even dependence on the data. In some examples, we may need that. And even if theta 0 is theta, this extra freedom is useful. So this is typically for non-parametric models, so where prior is often specified through a sequence, so situated on a sieve, a sequence of priors. So there is a discrete variable, j, depending on the sample size, which controls the size of the sieve. So in this case, this theta j, so this is typically guided by finitely many parameters. So it's a finite dimensional subset of the target space. And the prior sitting there, so that sequence, is concentrated on finite dimensions. So for example, on for function estimation, common method is to use basis expansion. So then you use a finite number of basis elements and to put a prior. So it's a finite dimensional prior. And then the computation, the update, posterior update, reduces to also finite dimensional. So this is often aided by conjugacy. So it suffices that immersion map, which possibly depends on j, and j depends on n, is only defined on theta j. So you don't need to define it all over theta. And it's also typical in such situation that the immersion map from theta j to theta, it takes you to the subset theta j to theta 0, it lands you in theta 0 intersection theta j. And this is a finite dimensional subset. So the whole computation, including that of immersion, is a finite dimensional calculation. That's important for practical applications because you want to keep it computable. And IP is an alternative random measure, so it should be independently justified by frequentist yardstick because we are inserting an extra degree of freedom, and even without that, still frequentist validation is important for several reasons. Now, there are some general argument I can give. So in some models, even without the restriction, you already may have good concentration property of the unrestricted posterior. It's only that it does not comply with the restriction and hence it's not nice. In such a case, the immersion posterior that we use can often, so immersion posterior is used to comply with the restriction, and it can, in many cases, it can just inherit the already available concentration. So on top of meeting that concentration property, it complies. So it's a desirable posterior to make inference. In other examples, so this happens in shape-restricted inference. In other examples like differential equation model or sparse high-dimensional model, the unrestricted posterior may not have enough concentration. The immersion technique is then used to rectify the deficiency. So it can work in both ways. So just quickly mention, this is a very simple result that says that, okay, if you have the unrestricted posterior concentrating, then the restricted posterior will also concentrate because, I mean, this is for projection posterior. In terms of that metric, that just is a consequence of the triangle inequality. So whatever rate you have for the posterior before applying the projection, the projected posterior still inherits that concentration rate. And this can be generalized when in many examples, we have an additional penalty term before you minimize. So that doesn't exactly minimize distance. And plus, the distance may be replaced by something more general, a loss function. So I have another result that says that, okay, if you minimize the loss function plus a penalty, and suppose loss function is satisfies this weak triangle inequality, so up to some constant it's this, and then you add a penalty, and then you assume that the penalty at the truth is less than the estimation loss, which is typically the case. Then also the same concentration is inherited. So the rest of the talk I will just give you some examples to show the usefulness. The first example is to show that conjugacy scope is a lot broader. So this is a familiar example where you have multi-dimensional response in linear regression. So here there is no conjugate prior if sigma is unknown and general. But if you use the immersion approach, you can use conjugate prior as follows. So what you have to do is to just view this xi beta as something general, mu I. So that's your general, the unrestricted space, and also make them free, the sigma I. So now it's a conjugate problem. You update mu I and sigma I, and then you will use immersion map as follows. So from this mu i's, you find some beta. So that's the mapping. From mu1, mu2, mu n, you map to beta by minimizing this map. And from sigma 1, sigma to sigma n, they are supposed to be the same. So you take the average to be the common sigma. So this way you can use conjugacy. It's very simple computation. Another example is logistic regression. There is also no conjugate prior. But if you use the immersion approach, what you do is just look at this extended model, xi follows binomial 1 pi, and then you do conjugate update using beta prior, and then you pull from pi's, you go to beta by minimizing this sum of squares, where logit means this function. Now, interestingly, this is not possible in the empirical for the empirical estimate, because see, yi, the response is 0, 1 valued. You cannot apply the logic transform. But pi is something strictly between 0 and 1, so this is applicable. Then I mentioned quickly another problem that was generated quite a bit of discussion. Diaconis and Friedman used this as an example to show that how poorly non-parametric Bayes was behaving. So it's a very simple problem, the location problem, where f is unknown distribution, symmetric, and theta is shift. So if you try to address it by usual Bayesian route, you'll have to put a prior on the symmetric f and then an independent prior on theta. And if you don't assume density, you probably use the Dirichlet process and then you symmetrize it. And then they showed that that leads to quite a bit of problem. The posterior can be inconsistent. But here is a very simple solution using the immersion posterior approach. So what you do is you ignore this, so you just think that x follows h. So h is this basically. So because there is no restriction, you put the Dirichlet process prior, which is conjugate, and then you use the immersion. From h, you go to theta and f by this immersion map. Theta is the median of h, and f is after you extract out theta. So you look at this operation, that gives you a symmetric distribution. So that would lead to consistent posterior. It will have semi-parametric, it will satisfy semi-parametric Bernstein-von-Mises theorem. So all problems easily solved. Then coming to my listed examples, monotone regression. So here we did some work. So we isotonize posterior, we put a prior on state functions and update the posterior, then isotonize posterior coefficients. Then we can easily show that because the explicit expressions are there, posterior contracts at the optimal n power minus 1/3 rate if the number of intervals you choose is of the order of n to the power 1/3. And then a more intricate question is whether the coverage converges, coverage of a credible region converges to the right place. So you take a 1 minus alpha credible interval for a function value at some specific point. Does the coverage go to 1 minus alpha? The answer is interesting. We can compute the limiting coverage, and it's given by this expression, some function a of 1 minus alpha. A is the CDF of this object. So you have two independent Brownian motions, condition on W1, and then look at this thing, where this is the argmin. So this looks like the Charnock functional. So this is a random variable itself. It's between 0 and 1. And the probability that the distribution of that is A. We call this the Bayes Charnock distribution. So then the coverage is not 1 minus alpha, but it's just A of 1 minus alpha. That may be different from 1 minus alpha. In fact, it's different from 1 minus alpha because A is slightly more concentrated in the middle than the uniform. So the limiting coverage is a little bit higher. But interestingly, there is no parameter involved. This is completely universal. As a result, you can start with a different coverage level, a little bit less, so that you end up with the target. So for example, to get 95%, you start with 93.2, I think. So that's quite interesting. This also goes on with monotone density and regression quantile. Regression quantile is the inverse function of the monotone regression function. Then I'm kind of short in time, so I'll quickly go over. I mean, the phenomenon is similar. In case of multivariate monotone, you put prior using state functions, but in this case, if you use a distance map to isotonize, that doesn't give you optimal solution. So you use a different map, and then you get a similar result on coverage, and so it's slightly more, and you can recalibrate to get to the right place. So we did this, tabulate this conversion table also. So all this can be implemented very easily. And you can also treat multivariate monotone density, same phenomenon. These are still being developed, convex regression. So I have some proposed solutions. So convex regression, you want to restrict to convex functions, but you can put prior on functions first, unrestricted functions, but you shouldn't start with state functions because you cannot change it to convex. But you can start with piecewise linear or higher order splines, and then you can make convex function by, for example, projecting the coefficients on the convex cone of coefficients giving convexity, or you can isotonize the derivative. So we're exploring both solutions, and you can also do some sort of kernel-based immersion where you look at fxi as the basic parameter, and then make them unrestricted so that you can give conjugate prior, and then you can do you can make it convex by some sort of map. So we are also trying to see what kind of property we are getting. So this is an example where the immersion map need not satisfy the idempotency condition. We're also exploring a problem on stochastically ordered distribution. So x to fx is the distribution indexed by a predictor x, conditional distribution. So this, instead of assuming some kind of parametric model or smoothness, you just assume that they're stochastically ordered. So if you have to do it through usual path, you'll have to use something like dependent Dirichlet process. That's very complicated. The expressions are very difficult to analyze. So you can use the immersion posterior approach. So disregarding this restriction, then individually put posterior, and then you isotonize these functions themselves. Like so that can be done, and we are about to get some interesting results. And then my next example is this differential equation models. So this is an example where likelihood evaluation is expensive. So what we can do is, so these are given by differential equations. So what we can do is, we can put a prior on the function without assuming it's a solution of differential equation. So this can be done by splines with sufficient high degree. And then we use, we used spline expansion, finitely many splines. And then we use a projection. So projection can be chosen like this. So in the ODE, the basic ODE model, the derivative is supposed to satisfy this equation. So when it's from the model, this will be exactly equal to 0. So this will vanish. So it makes sense to minimize this with respect to, so you put a prior on F, then that's conjugate, and then you get a posterior sample. From F, you get posterior sample of F prime, and then you minimize, so you get a theta. And that induced posterior satisfies some Bernstein-von Mises theorem, so it has justified Bayesian uncertainty quantification from Frequentist point of view. And you can also do other projections to make it efficient. There is a loss of efficiency if you use this, but this one is more efficient, but it's more computationally heavy because we'll have to solve actually the equation, but it's still a lot less expensive than evaluation of the likelihood. Okay, so this is I already told. We can also treat higher order OD, GLM, PD. So the basic idea is the same. It's the technicalities that are different. Okay, and then now my final major example is high-dimensional linear regression. So sparsity is needed to make inference in high-dimensional setting, but that also makes things complicated because if you have to comply with sparsity, you cannot use most basic priors. There are alternatives, of course. There are ways to do in Bayesian inference, but none of these are simple, and especially uncertainty quantification cannot be validated from Frequentist point of view. So the usual Bayesian approach use some mechanism to make sparse data in the prior, then posterior is complicated. Now, in the IP approach, what we do is we disregard sparsity, just put a conjugate prior on theta. And sigma is the standard deviation. On that, you also put a prior. And then you use an immersion map to make posterior samples sparse. So this immersion map is motivated by the lasso operation. So that makes it sparse, and then you look at the induced posterior. It has some interesting properties. So for example, you get optimal recovery rate, just like you can do it much more computationally intensive Bayesian methods. Optimal prediction rate, sign consistency, selection consistency. All the conditions that we need are exactly the same conditions that lasso needs. So it's very, very well accepted in the literature. And we can also do uncertainty quantification, but not using this immersion map. We have to use another immersion map. And that's the debiased immersion map. I don't have time to go to the details. So we can apply, even if P is not high dimensional, and then we can find the limiting posterior distribution that has some interesting structure. But let's keep that. And we can do other high dimensional examples. So introduce group sparsity or additive non-parametric regression or generalized linear models, graphical models. All these have some form of sparsity that we can use the immersion posterior approach to very nicely handle this and derive optimal Frequentist properties. this would be the last example about to finish. So this is not a solution. This is just something that needs to be addressed. So consider situations where you have each xi observation has its own parameter theta. All you know is that these theta are kind of similar. They come from the same distribution. They are random effects. You don't know this g. So what you do is typically Bayes, if you do, you put prior on g or do empirical Bayes, but then they overshrink. So how to incorporate this qualitative information in the prior? That's not clear, but that's something food for thought. Okay, I think that's all. Thank you for your attention.
Thank you very much. Questions? Yeah, please.
Thank you very much for your talk. I'm wondering, are there any general techniques that one can use to show posterior consistency or uncertainty identification results in all these different settings? Or, I mean, is it the case where you have to analyze each immersion posterior?
Yeah, that is a very important problem. Very important appropriate question. So when we have this traditional Bayesian posterior, we have we can give some general theorems, especially for concentration rate in terms of entropy, prior concentration we can characterize. Every example still has to be worked out because these estimates have to be obtained, but we have a path to do that. In case of immersion posterior, unless it is the concentration inherits from its parent, if you have to do it like in differential equation models or sparse high dimensional models, the unrestricted posterior does not have that concentration. So it's something that the IP has, it's not coming from there. So it has to be established directly. And so far we do not have any general theory that handles. So that you can say that that's one of the aspects we still have to think about. Maybe in the future there would be some sort of general theorem that will emerge, but that's not unusual. So even, we are primarily looking at frequentist properties, and in high dimensional models, if you look at estimators, empirical estimators, so those are treated separately often. Sometimes later on there is some sort of umbrella theorem that encompasses several of them, but generally speaking, you will probably have to address things separately. And for uncertainty quantification, I'm pretty sure it's separately addressing would be the more common thing than general approach.
Follow-up question. In the case of sparse linear regression, does the debiased uncertainty quantification map is that only dependent on X, or does it depend?
It depends only on X. Okay. Yeah, right. But I didn't have time to go into the details. So for sigma, the scale, so we need to use a data-dependent immersion map we just need to make it consistent. But in the high-dimensional setting, if you use just the basic conjugate prior, then it is inconsistent. And if it's inconsistent, it's not a good starting point. But it's very easy to make it consistent by an immersion map. Just you scale it so that its posterior expectation is set at the right place. Once you do that, then the whole posterior is consistent. So that's what you will need. In contrast, in other Bayesian methods, so for example, spike and slap prior, so there's this concentration established, but they have to use that it's known. I mean, it's not really, that proof cannot be expanded to cover unknown sigma. You can, but not using that technique, and you will have to give up uniformity over beta. So there are different but those are too technical to discuss in this talk.
One last question about that model is, do the uncertainty quantification results depend on the true distribution of the covariance of X?
It just needs to satisfy some general conditions, just like what you need for the, the corresponding frequentist analog. So, for example, the DBAS lasso estimator that is used to construct asymptotic confidence intervals. So, the same conditions would be needed here as well. But it's general, it's not a specific assumption on X. Yeah.
So maybe a question related to kernel method. So do you think that the immersion posterior can be interpreted from kernel perspective, or mapping probably distribution to some Gaussian Hilbert space, or?
Gaussian, well, often we have conjugate, especially in function estimation, we often put priors through this basis expansion with normal coefficients. So those posterior distributions are Gaussian processes. So we often start with Gaussian process and apply, but in general, the concept does not have to be related to Gaussian process. Gaussian process will obviously be, as an important device, will appear in many contexts, but it doesn't have to be that.
Yeah, I was just thinking about that one can use kernel method to compute the immersions directly.
So immersion map is something that you specify, and you typically specify something that is fairly simple because that's what you want to work with. It's up to you. So that's an extra degree of freedom. And so of course you choose something that you can compute. You don't choose something that you cannot compute, right? So, and at the end of the day, you want to show that it serves some purpose, like validating frequentist uncertainty quantification, convergence. So if it doesn't do that, of course, you don't use that. You use something else that will work, right? So I want to make this remark. It's important that it's not that this is being used the first time. In some form or other people have sort of used something like that, so especially the projection approach. So Lean and Danson, for example, did this for monotonicity, and in the high-dimensional space also we came to know that there are some people. But what we want to give is some sort of a general framework and umbrella, and this whole thing can be viewed within this, and just as an extension of the Bayesian paradigm that would be useful when you need it.
And I was just going to ask, one of the main motivations for people who adopt Bayesian methods is the coherence principle that you get. Your resulting inference is coherent. Do you retain that coherence for these methods?
That we have not checked. It may not be many of these extensions, but as I mentioned, it satisfies the likelihood principle. Yeah. So at least it's not, and it's, so for example, the most commonly adopted extension of Bayesian method is empirical Bayes, which violates the likelihood principle. So, so in that sense, it's better positioned, but it may not, obviously, even if you use non-informative prior, improper prior, that will also violate some of the, so we cannot expect everything will be obeyed, but many of these things will be fine, some will not. So I don't know exactly about coherence. It's not really my expertise.
Great. Well, if there are no more questions, let's thank Subhashis again.